Good day, Doctor. We are here to present our project for Milestone 4. I'm Yiling. The objective of our project is to implement LANet 5 model on STM32F446RE nuclear board to perform image classification with high accuracy. The second objective is to compare LANet 5 inference time between F446RE nuclear board and CPUs of other platforms. In this project, we will be using pre-trained LANet 5 model with MNIST datasets. Here's the architecture. The input is a grayscale image with channel value of 1. It mainly consists of 2 convolutional layers, 2 max pooling layers, 2 fully connected layers, and softmax classifier. The convolutional layer contains sets of filters. Each filter will be convolved with the input volume to compute an activation map, which is the feature map that made up of neurons. After that, pooling layer will help to reduce the parameter computation by downsampling the representation. In here, we are using max pooling, which is to select the brighter pixels from the image. Then, fully connected layer is to connect all the activation unit between layers. Lastly, softmax will classify object. These are the softwares that we are using. Caffe is a deep learning framework. It is needed when we run the classification in Google Colab and when we quantize the pre-trained model. It is needed 2 for us to generate the C and header files, which we will be using in STM32Cube IDE later. The script to quantize the model and the script to generate C and header files are Python scripts, so we need to install Python. STM32Cube IDE is a C or C++ development platform with peripheral configuration and code generation that supports STM32 microcontrollers and microprocessors. The hardware is STM32F446RE nuclear board. Here's the project flow. First, we need to install and set up Caffe, then download pre-trained LANet model. Then, use Google Colab to do classification to prove that the pre-trained model is working well. Then, quantize the model in terms of weight and bias. After that, use script to generate C and header files from the quantized model. Set up project in STM32Cube IDE. Then, include C, header files, CMSIS-NN and CMSIS-DSP packages into IDE. Then build and upload nuclear board to perform image classification.
My name is Wong Yixiong. First of all, I would like to thank our group member, Yiling, for providing us an informative introduction. Now I will discuss about the data preparation. Like I mentioned earlier, we use Caffe as our deep learning framework. Caffe is a deep learning framework characterized by its speed, scalability, and modularity. Caffe works with CPUs and GPUs and is scalable across multiple processors. Model training is one of the crucial steps in our project. We try to train the model locally, but we found out it is time-consuming. Due to time constraint, we choose to use a pre-trained model which is available in Caffe directory, since our final goal is to deploy the LANet network on nucleo board. However, I will still discuss about the overall flow of how model training is conducted to gain a better insight. Before training our model, we need 2 files, which are MNIST train and MNIST test in LMDB format. These 2 files can be generated by using the script, which is available in Caffe root directory. After that, there is a file called LANet train test prototest, which defines the LANet network. This file basically contains all of the necessary information about the layers configuration and what are the layers needed in LANet architecture. For example, data layer, convolution layer, pooling layer, and fully connected layer. The activation function used also well defined in this file. Next, we need another file which called LANet solver prototest, which defines the LANet solver. This file basically contains the information such as the LANet network defined and hyperparameter needed to train the model. Besides, this file also defines the display and checkpoint snapshot as well as solver mode used to train the model. This is the example of the content in LANet solver prototest file. As mentioned earlier, the file which defines the LANet network is included in this file. In this project, we are not going to explore deeper into hyperparameter tuning. We can choose the time interval for snapshot. If anything broken halfway, we are able to resume the model training through the snapshot we saved. Lastly, we can define the solver mode used, which can be either CPU or GPU. After preparing all of the necessary files, we can start to train our model using the command shown. The circled part is the script used to kickstart the training, where the argument required is our linear solver prototypes. Once the training is completed, the model will be snapshot in cafe model format. In order to test the accuracy of our model, we use Jupyter Notebook to run the inference. By using 10,000 images as the test inputs, the model is able to predict 9,919 out of 10,000 images correctly. The accuracy is out to 99.19%, and the inference time takes about 19 seconds to complete. Although the model is performing well, we are not going to implement the model directly on our nucleo board. We will quantize the model by using the script available in cafe directory. Moreover, we will use another scripts to generate the input files which are needed to deploy on the board. The input files generated are main.cpp, parameter, and web header files. By having all of the necessary files, we are going to implement the model on our board.
So to generate those files, firstly, we need to use a Python script to convert Linux Cafe model and its prototypes into Linux speaker files and quantize Cafe model. Then we need to use another script to convert those Linux speaker file and its quantized Cafe model into C++ and headers files. As you can see, this file contains all the vegs and biases for every layer of Linux model. Well, for this file, it contains all the parameters for Linux model, such as the input dimensions, input channel, kernel dimensions, and so on. The content of main C++ file has been included into main.c file. This main.c contains of two main functions, which are the run_nn and get.prediction. As you can see, run_nn consists of CMSIS-NN Library functions. To have a clearer picture on this, we can have a look onto this slide. Every single layer of Linux model are corresponding to one CMSIS-NN functions, which have been implemented for convolutional, max pooling, fully connected, ReLU, and softmax layers. In our project, we are going to upload image onto nucleo boards in array format. To do so, we have used a Python script to convert a total of 10,000 MNIST test images, which is in 8-bit format, into several input header files. Inside this file, they contain MNIST images in array, which are in the format of 7 bits plus 1 signed bit. After integrating all files into STM32Cube IDE project, we are ready to build and run the program on the nucleo board. As you can see, the classification result can be displayed via Qt terminal. Text picture acting as an example. It has the highest possibility for class 0, which is correctly predicted by the Linux file on nucleo boards. As a result, quantized Linux file on nucleo board has obtained a very high accuracy of 99.1%, which is comparable to Linux file without quantize. Below picture shows some of the wrongly predicted examples. On the other hand, our nucleo board has obtained the lowest inference speed, which is 1.1 frames per second, when comparing to Linux file running on other platforms. This may be due to its low core number, low frequency, and its architecture itself. As a conclusion, Linux file has been successfully implemented on our Cortex-M3 nucleo board with the help of CMSIS-NN Library. Thus, our objectives have been accomplished, and the presence of CMSIS-NN itself do make the deep learning implementations on ARM Cortex-M processor more feasible. So that's all. Thank you and have a nice day.